Hey everybody, welcome. Welcome to another live stream from this channel. Well, welcome to the second video in this Let's Do Labs Together series. Today, we're going to be running through another packet tracer lab. In the lab, I'm going to explain my way through the configuration and troubleshooting of various Cisco routers and switches. Now, initially, this series is going to focus on packet tracer labs. The reason for that is because it's very easy to acquire and download and share. But I am definitely happy to do more complex labs together if that's something you'd be interested in, using GNS3 or EVE-NG. If that's something you would like, please mention something in the comments below, and I'll see what I can do. Also, feel free to suggest labs if you know of various labs that you can acquire without violating any sort of copyright, of course. But if you know of those labs that you can just download and acquire and work through, I'm happy to run through some of those. Feel free to share those links in the description. That said, if you're joining us in the live stream, welcome. And if you're joining us in the recording, I'm going to add timestamps to this after the fact, so feel free to use that to jump around if you need to. Now, the plan for today is to run through one of Keith Barker's labs. Now, Keith Barker, if you don't know, so I'm going to go to share my screen. Keith Barker has a website, thekeithbarker.com. Keith himself, he's been a Cisco instructor for years and years and years. In fact, I initially learned my Cisco content when I first got CCNA certified, I think over 10 years, 15 years ago, man, I don't know, at least over 10 years ago. I was initially learning that stuff off of Keith Barker's original CBT Nuggets videos. So Keith has been in the industry for a very long time. He's very excited about what he has to teach, and he has a lot of cool content. The lab we're going to be working through today is actually one of his labs. So if you go to his website, thekeithbarker.com, that's the URL right there. Make sure the screen share, yep, okay, cool. If you click on downloads right here, that'll scroll you down to this section of his website, and this is where you can download all of Keith Barker's free packet tracer labs that you can work through if you're studying through the CCNA. Today, so we did this one last week, Thursday of this week, and today we are going to be doing this guy right here. So feel free to download this guy. There's also a link in the description if you want to work alongside with us, or if you're watching this in the recording, feel free to download and pause this video and work through the lab yourself, and then come back and see how we go about doing it. Now, cool. So one of the things that I really like about Keith and Keith's teaching is how passionate he is about the content that he's teaching. When you're studying for the CCNA, there's a lot to get through. The CCNA is not a small certification by any means. And having an instructor that you can use that is excited about what he's teaching and passionate about what he's teaching is a huge benefit to make that large undertaking of the CCNA that much easier. So highly recommend Keith's stuff. A large part of it is because of how passionate he is about what he's teaching. In particular, so this is his YouTube channel. You guys need to make sure you're subscribed to that guy. But in particular, there's two playlists of his that I want to share. First, this is his what he calls his master CCNA playlist, and if you see, there's 150 videos or so covering a variety of topics that all fall within the CCNA. So if you're studying for the CCNA, definitely add this to your repertoire of what to study off of. I would say if there's any topic that you're still working through, still kind of trying to understand, whatever resource you're using now, if there's something confusing about it, jump onto this playlist, take a search, and see if Keith has already produced a video about it. Highly recommend his content. The other playlist actually works alongside with the labs. Each of these labs has a video where Keith himself walked through it himself, and that's what this second playlist is right here. I'm going to add a link to both of these in the description afterwards, but you can take a look at these. So after going through this stream or this recording, if you want to see how Keith walks through his own lab, feel free to look it up in this playlist right here. With that said, I don't think there's anything else insofar as announcements, so we will get right to it. So let me just quickly check in with the chat, see if I've missed anything. Hello everybody, welcome, awesome. Sound is good, PT is good, fantastic. All right, with that said, let's go ahead and get into it. So just to prove, we are doing the exact same lag that you would get from Keith's website. Again, this is the one we'll be doing today. I'm going to go ahead and download a new copy of it. If you open this guy up, there'll be two files in there. A PDF file, which is a copy of the instructions from Keith Barker. It looks like these are the objectives of this particular lab. And then the other file is the actual packet tracer lab itself. If we double click that guy, Packet tracer will open up. Now, one thing again I'm not going to cover in this video is how to install and acquire a packet tracer. There's been a ton of videos that have been created on how to do that from people that are more familiar with packet tracer than me. So definitely look those up if you're interested. I am currently running packet tracer version 8 point something or other, 8.0. I believe Keith recorded or created all these labs in packet tracer version 7.3. So if you're doing this lab in packet tracer, make sure you are using a version 7.3 or higher. Do not try to do these on older versions of packet tracer. Likely you run into some issues. So this is the lab that we have in store for us today. Now Keith added the instructions, so if we open up PDF, the instructions as a background image in this particular lab, so that's kind of convenient. It's all in one place. Now since we have the PDF open, I think what I'm going to do though, just so that we can see everything in one side, is I'm going to move everything down and put this guy there, that guy there, there. And so now we can see everything on the left side of the screen, including our objectives. Cool. So with that said, let's get into it. And so I'm just going to start configuring it. Now, one of the things that I'm a big fan of when you jump on a lab, especially somebody else's lab, something you haven't built from scratch, is the concept of look before you leap. The idea is don't start making changes until you really understand the topology that you are working with. So before I even worry about what I have to do to actually accomplish this lab, I'm just going to look around and explore. So let's start with our PC. So our PC is currently configured with the IP address 10.10.0. Sorry, that's the gateway, is 10.10.0.3. The IP address of the PC is 10.10.0.10, and this is a /24 network. More than likely, since these are layer 3 switches, that 10.10 network ends on those layer 3 switches. So let's jump on that guy to make sure. I'm going to do a show IP route, and this is telling us indeed the layer 3 switches have a connected route for the 10.10.10 network, presumably on this side, which is going to be VLAN 10, and then a 10.20 network, which presumably, and we'll verify this, is going to be this network over here. Now, because I'm not one of those people that can just memorize a bunch of information, I do like to annotate. So I'm actually going to add a little rectangle over here so that we can identify what networks each of these are. I'll make that a little bit bigger, actually. And then I'm going to add a little bit of a note. And this will make it a little bit easier for us. So we know this is the 10.10.0.0/24 network, and we know this is the 10.20.0.0/24 network. Actually, I don't think we actually verified that it was the /24. Oh, yep. Yep, it is. Show run section interface VLAN 20. It is a /24. Cool. So something else we can notice from here, notice interface VLAN 10 is running HSRP. So if you recall, the default gateway of the PC over here, which was in the 10.10 network, was 10.10.0.3. That's the HSRP shared address. So what that means is both these multi-layer switches, that's what the acronym MLS stands for. These are, it's another term for a layer 3 switch. Both of these switches are running HSRP and are essentially sharing an IP address, this guy, 10.10.0.3, so that PC1 has a default, redundant default gateway it can use. So that's a concept, that's a technology. HSRP stands for Hot Standby Routing Protocol. It falls within a suite of protocols known as First Hop Redundancy Protocol, FHRP. It's just a way of having redundant default gateways. Cool, so that's the PC gateway suite. And just to be sure, let's make sure we can ping the PC from our switches. Cool, so that looks good. We're happy with that. So this tells us that we have connectivity from the layer 3 switches to the PC. Now that also tells us I'm not going to have to worry about this switch. If I can ping through the switch to the gateway, then I know that the switch is configured correctly. Now we can jump on and make sure everything's on VLAN 10 if we need to, which seems to be the VLAN in use on this side of the layer 3 switches. But since the ping went through, I know everything layer 3 and below up to this, up to that, say, set of devices is good to go. So now, now let's jump onto the router. And I'm actually going to make this guy a little bit bigger because that actually ends at the router. Cool. So let's close the PC. Don't need that. And we will move that guy over here. So if I jumped on the router, why can't I jump on the router? Oh, yep, I was still in editing the box mode. Okay, so here is the router. So let's take a look at what we have. So the router has two interfaces. One of them, the 10.20.0.1 interface, that is going to be the what is that, gig 01. It also confirms it right here. The left interface of the edge router. And then the other one is gig 00. It's going to be the network on the where the server is. And just like before, I'm going to add a little note just to make it a little bit easier. And we're going to make this, it is a 23.1.2. We don't actually know that it's a /24 at this point, so let's verify that. Show run section interfaces. It is a /24, cool. But this tells us the network that is on the right side of the router, off of gig 00 of the router. I'll also mention, if you guys have any questions, feel free to just throw them into the chat room, and I will. I've got the chat room up on another monitor, so I can see those questions as they come in. Also, I am still kind of getting over a head cold, so if I sound all nasally, I apologize. With that said, let's continue. Cool. So we've identified where all the networks are. One thing. So let's take a look at the routing table of the router. So it looks like the router, interesting. So the router is running OSPF. That's what that O indicates. And that's where it's learning of the 10.10.0.0 network. That's the network on the other side of the layer 3 switches. So from that, we can learn that the layer 3 switches and the router are doing OSPF with one another. Here are the connected routes, obviously, for the router itself. And then the router has a default gateway pointing out to, this is probably an address that doesn't exist, but it's out this interface. So you could presume that the internet exists somewhere out over here, is sort of like what the lab is trying to simulate. Cool. Okay, so with that said, let's get into it. So the lab objectives, actually one more thing I want to check is the server IP addresses. So the server IP addresses 23.1.2.2. And I'm also going to add that as a note in our little diagram because I will definitely forget the server's IP address later on. And the interesting thing is actually right here. So in this particular lab, you'll notice that the lab objectives indicate that the web DNS server, which is the only server on our topology, should have no default gateway configured. And indeed, right at the moment, there is no default gateway. Now, the role of the default gateway is to speak to something on a foreign network. So without a default gateway, you can only speak to people on the local network. So this is actually a very significant clue for this lab. This tells us that, excuse me, this tells us that this web server is only going to be able to speak to anything on the 23.1.2 network. It's not going to be able to speak to anything on any other network because it doesn't have a default gateway. Now, theoretically, I could configure a default gateway, and the ideal default gateway would be the edge router, but it seems that's part of the lab objectives is to not do that, to see if we can find a way to get the PC to open up a web page on our web server without configuring a default gateway on the web server. The point of that is it's going to force you to use NAT or PAT or address translation in order to make it look like this PC is actually coming from an address in the IP address network that the server is able to speak to, meaning the 23.1.2 network. So we'll be configuring that in a moment regarding that. To start, let's make sure that so just like we pinged from the PC, actually we pinged from the switches to the PC to see, to make sure connectivity over here worked. We're going to do the same thing. We're going to ping from the PC to the router, the edge router, to make sure we have connectivity all the way through those devices. So I'll jump on the command prompt and I will ping the router, and the router IP address that I want to ping is this guy right here, 1020.0.1. So I will put that over here. Cool. The first one worked. The rest timed out. I'm going to call that a fluke. We'll do it again. Sweet. So this tells us that we have connectivity from the PC to the router. But this is still testing a ping of this, this interface of the router. Let's see if we can test from the PC to the other interface of the router, which was, if I scroll back up, this guy right here. So again, I'll open up my PC and I'll do a ping 23.121. And you'll see here something interesting is going on. I get a destination host unreachable. So this tells me the PC cannot ping the other side of the edge router. Now, interestingly enough, take a look at who gave me the response, 10.10.0.11. If you recall, that's actually the IP address of the layer 3 switch. So if we jump on the layer 3 switch and I do show IP route, just like we did before, we could see that the layer 3 switch only knows of two networks, the 10.10.0 network over here and the 10.20 network over here. The layer 3 switch does not know about the 23.1.2 network. What that means is when we are pinging from the PC to this interface of the router, that interface was 10.20. something or other. The switches knew about how to get to the 10.20 network, so we're able to forward that packet to the router. But when this PC tried to ping this interface of the edge router, which was the 23.1.2 network, the packet got to one of the switches, whichever one was acting as the gateway at the time, got to one of the switches, and that switch was like, I don't know how to get to the 23.1.2 network. I'm just going to drop the packet right here and let you know that the destination that you're trying to ping is unreachable. So the problem there is that our layer 3 switches currently don't know of this network right here. Now, there's a couple ways we can solve this. Obviously, we can give these switches a static route, be like, hey, to get to that network, go to the edge router. That's option A. We can have the edge router, remember OSPF is going on between these routers. We can have the edge router advertise the 23.1.2 network to our switches. That would also absolutely work. But the third option is to have the edge router advertise to these switches a default route. Now, given the lab setup, this is sort of simulating the internet, and theoretically there's thousands and thousands and thousands of different networks on the internet. So it wouldn't make sense to try and add individual static routes or advertise individual routes from the edge router for each of those networks. So instead, I feel the best option here would be to have the edge router advertise a default route to our multi-layer switches, so that the multi-layer switches will have a default route that says if they're trying to get to a network they don't know about, they're just going to send it to the edge router and let the edge router deal with it. Now, we could also do this with static routes on both of them, but I like doing less work if I have the option. So I'm just going to tell the edge router to send a default route to the layer 3 switches. So let's get rid of my pen. I'm going to leave that right here just so we can see the transition. I'm going to go to my edge router and we'll take a look at what we have going on with OSPF. So it looks like right at the moment, our edge router is running OSPF, has everything in the tens slash, this is the wildcard mask of /8. So anything that starts with 10 is being advertised into area 0. But you'll notice there is no indication of a static route, rather of a default route being advertised. So we can add that configuration. So router OSPF1, and the command for that is default information originate. Now, if I hit question mark here, you'll notice that that's the only option I have. So from here, I would just hit enter. On a real Cisco device, there's two options here. If I just do default information originate, that's only going to advertise a static route if this router has a default, that's only going to advertise a default route if this router has a default route, which at this point it does. However, there is normally an additional option right here where I could type always on a real switch if I wasn't doing a packet tracer, on a real router rather, if I wasn't doing packet tracer, where I can force the advertising of a default route regardless of whether the local router has a default route or not. But since this is packet tracer, we don't have all the commands available. So this is the only option it gives us, but that is going to be enough because this router happens to have a default route. It is now going to send a default route to the multi-layer switches, to layer 3 switches, and you actually see this apply. OSPF is generally pretty quick. If I do my show IP route again, you'll see now my layer 3 switch knows of a default route. And if we go back to my PC, which I believe I closed, oh, there it is, you'll see now I am able to ping my router. So now that the layer 3 switches know how to get to the 23.1.2 network, they'll forward that packet to the router, and in this case, the router itself is going to respond. So we have now confirmed connectivity from our PC through to this interface of our edge router. The last thing we want to do is to confirm connectivity all the way to the web server. Now, because of the other objective, obviously this isn't going to work, but just for kicks, let's go ahead and show you. Let's show you the failure so that you can see the success later on. So the web server IP address is 23.1.2.2. So let's just shoot a ping over to the web server. Obviously at this point it is going to fail. Now the interesting thing is to understand where the failure is happening. So we know the PC is able to send something to this interface of the router. The issue, rather, which should also tells us that the PC is going to be able to speak to anything in the 23.1.2.0 network. So this ping is actually getting to the web server. The problem is the web server is now trying to respond, sending packet back to the destination 10.10.0.0 something. But that IP address is a foreign network from the perspective of the web server. And remember, our web server doesn't have a default gateway, which means our web server only knows how to communicate with other stuff on its local network. So what's happening is the packet is getting to the web server, but it's not leaving the web server. It's not going back out to PC1. That's what we're going to have to fix. Now the way we're going to fix it is we're going to make it look like PC1 has an IP address in the 23.1.2 network, which was the whole point of this particular lab, is to implement NAT on the edge router such that the PC1 and the server have communication. So the goal is to make PC1's traffic look like it's coming from 23.1.2. something. So that's kind of where we're at with the goal. Now there's two ways that we can do this. One of the ways involves using a static NAT. We can tell the edge router that whatever traffic comes from the PC's IP address, 10.10.0.10, I believe, statically translate that to a different address in the 23.1.2 network. The other way is we can tell the edge router that, listen, anything coming from the 10.anything networks, dynamically path them to a different IP address on the 23.1.2 network. Both of those are successful ways of solving this problem. And just to show you both sides of it, I'm actually going to configure both so that to prove to you that they'll both work, and show you there's always, with networking, there's often kind of multiple ways to skin a cat, you could say. There's always different ways, multiple ways to solve particular problems. So we're going to show you both of those ways next. Now, since we're doing a static NAT configuration, what I like to do is some years ago I wrote an article. Let's pull that guy up on my blog, Practical Networking is my blog, that outlined how to configure NAT on a Cisco iOS router, and it goes through all the different types of NAT you can configure, and there's pretty pictures and the configuration and explanations of each word, and showing you packets are going inbound, outbound, all that fun stuff. But all the way at the bottom, if we go down to the summary, there's this cool little table which is sort of a summary cheat sheet of the configuration for every type of NAT on a Cisco router. Even though I wrote this article, I still use this anytime I'm configuring NAT as my sort of indication of what the commands are, just in case I forget something or whatever. This cheat sheet, if you click any of these, they'll jump back up to the explanation of how it all works, and you can see all the packets and all that fun stuff. But we are going to use this cheat sheet to configure NAT on our router. Now the way NAT configuration works is anytime you configure NAT on a router, the first thing you do is you start by telling the router what interfaces are inside and what interfaces are outside. That's important because if we go back to our topology, you and I can look at this, look at this pretty map and determine that this is probably the outside interface and this is probably the inside interface. But the router doesn't have a way to automatically know that. So you have to tell the router what interfaces are inside or outside. So we'll start with doing that. And then we're going to first solve the problem configuring a static NAT. And then we're going to solve the problem again using dynamic path. But to start, we're going to start with static NAT. And I'm going to put that right here so we can look at it while we are configuring. Cool. So we will minimize this guy. We'll stay on the edge router. Awesome. So let's take a look at the interface configuration now before we add anything to it. So what we're going to do to start is telling the router which interfaces are inside and which interfaces are outside. Now, one thing I also like to highlight when I'm doing these kind of lab walkthroughs is understanding the difference between a device's configuration and a device's operation. As an engineer in the field, this is a very important distinction that you're going to have to understand. Many times you can look at the device's configuration and be like, okay, it's configured to do something, but the operation is doing something else. And so understanding when you're looking at a command, whether it's telling you the configuration or operation of a device is very, very important. With show run, it's only telling you the configuration of the device, not the operation. And you'll notice at the moment there is no NAT anything configured. To verify NAT interfaces, the operation command you want to use is show IP NAT statistics. Right now, this command is empty because there is no NAT configured, but I wanted to show it to you first before we go into actually configuring any things. So we are going to jump on interface gig 00, and we're going to tell this interface that it is the outside interface. So IP NAT outside. And then now if I go to show IP NAT statistics, you'll see the output of this command is going to change. This is where I type the command. Now we get all of this. And the important part of that part is that line right there telling us that gig 00 is indeed the outside interface. Excuse me. So let's now do the same thing in gig 01 for the other interface. Gig 01 is the IP address on the 10.20.0 network. That's going to be, oops, I typoed something, int gig 01. IP NAT inside. That's going to be our inside interface. And again, notice before I had nothing listed as the inside interface. And now I've got gig 01 listed as the inside interface. So that takes care of the first part of configuring inside and outside interfaces. In my little chart over here, I had inside twice just to show you if we had more interfaces on this router, you can add as many as you want as the inside interfaces. Cool. So now we're going to actually configure the static NAT on the router. So if I do a show run, and for section IP NAT, you'll see so far all we have are the IP NAT inside and outside. Now the way the section filtering works is it's literally looking for the string IP NAT. And that only exists in these two commands we just added. The reason there's this weird spacing is because that actually exists inside the interface itself. You can see this if I look at the full interface configuration itself. In any case, we're going to use this a few more times. I just want to show you what's going on here. This isn't a command you can add directly from global configuration. It must be added within an interface. But I did want to explain what's going on here because we're going to be using this show run command a few more times. Show run section IP NAT. So right now we don't actually have a translation configured. We just have the inside and outside interfaces configured. So we're going to do the translation next. And the command for that is IP NAT inside source static. And now we mentioned the inside local IP address. So that's going to be PC1's IP address itself, 10.10.0.10. And then now we have to mention the inside global IP address. Now, the lab didn't provide instructions on what we should use. You and I know, because the web server doesn't have a default gateway, that the IP address we use for NAT must be something in the 23.1.2 network. So we're just going to pick something. We don't want to pick something that's already in use, so we're going to avoid .1 because that's the router's IP address. We're going to avoid .2 That's the web server's IP address. So we're going to go with 23.1.2.10. We'll try and match the 4th octet of the PC, because why not? I'll hit enter here, and then I'll do my show run command again. So show run section IP NAT. So this is telling us we have something configured in our running configuration. But again, this isn't showing you the operation. To see the operation of NAT, you do show IP NAT translations. This is showing us a translation table. And what this line is indicating is that anytime the router sees an inside local IP address of 10.10.0.10, it's going to translate that to 23.1.2.10. Now this particular line showed up. Oh, hi Muthu, welcome to the stream. This particular line showed up the moment I configured this static NAT. You're going to see more output in this particular command once I actually start sending traffic through this particular translation. And I'll show that to you in a second. So let's go, where is our PC? There's our PC. So you'll notice before the ping, oops, scrolling down, the ping to the server did not work. Let's put this over here. Now with our static configuration in place, you'll see that the ping is going to work. We are successfully getting a response. Now if I go to my show IP NAT translations table again, I'm just going to hit up arrow, hit enter. You'll notice additional output in the command. It's showing me that a particular ICMP packet with this particular inside, this particular inside local was translated to this particular inside global. It had an outside local of this, and the outside local was translated to that, but obviously you'll notice these are the same IP addresses. This is telling you we only translated one side of the packet. Meaning, when the packet was going this direction to the web server, it had a source of 10.10.0.10 and a destination. That's the packet right here. Look at my cool. So this is the packet when it left PC1. Had a destination of the server, so 23.1.2.2. And then after the translation, we'll go with a different color. After the translation, so the packet over, oops, not there. The packet over here, rather. My cool little flying envelope had a source of, oops. Sorry, I don't have my pen, so I'm writing this with my finger. So I apologize for the legibility of this. We changed it to 23.1.2.10, and the destination didn't change. 1, 2, 2. So this is what's going on in this table. Initially, the packet looked like this. This was the inside local. This was the inside, rather the outside local. This is the packet as it appeared on this side, the inside network, the local perspective. Then on the other side, the source changed to 23.1.2.1 because of our configuration. You can kind of see it behind right here. We told the router to change that source, and the destination did not change. So this is reflecting that the source changed, and this is reflecting that the destination did not change. But that's why there's these 4 columns in this output showing you everything that would have changed in this particular packet. Oh, cool. Okay, cool. So that actually solves the problem, right? The PC can now ping and access the server. That was us solving it with show IP NAT. I'm going to now show you how to solve it with a dynamic path. Actually, first, real quick, I want to show you this command one more time. These entries reflect live traffic, so you'll notice now that it's been a few seconds that those entries have been purged. Obviously, this entry is a reflection of the configuration, so that's still going to be in place. But if we do a TCP packet, let's say port 80, and now we look at our translation table, we'll see kind of the same thing as before. We'll see that the inside local of the PC1's IP address, source port 1025, was translated to the source 23.1.2.10, just like we configured it to. and there's again a reflection of the source port. So if this TCP port 80 packet got through, this tells us, going back to the lab objectives, that we probably will be able to access the web page on that server. Now before we do that though, I do want to show you, you can also solve this using a dynamic path. So let's go ahead and get rid of, let's go back to here. Cool. So let's get rid, so we'll do a show IP NAT translations just for kicks, and I'm going to get rid of my NAT statement. So this is the static NAT that we had configured. So this is the command that I'm going to remove. So I'm just going to copy it. Rather, I'm going to type in no. Then I'm going to copy and paste it to get rid of that line. Now, if I do show IP NAT translations, you'll see there's currently no output in this particular command. That's the same command we were using before because I removed the only NAT statement that we had configured. And now if we go back to our PC, we'll start with a ping. And the ping is going to fail for the same reason as before. Cool. So now let's solve it using a dynamic path. Now, if we scroll down over here to our little guide, you'll notice that there are two ways to do a dynamic path. The difference between these two ways is one of them is doing a dynamic path to a NAT pool, and the other one is doing it to the interface IP address. So if you recall, a dynamic path is a translation which takes any set of IP addresses. In our case, we're going to configure anything in the 1010 network and translates it to use one or at least far fewer addresses on the other side. One option is to reuse the IP address of the edge router. That would be an interface-based dynamic path. This is actually what pretty much all small home office routers are doing. So you live in a house that has a Wi-Fi router that is likely connected to a modem that is likely connected to the wall, to the internet. Well, that Wi-Fi modem is translating all the private IP address at your house into the outside interface IP address of your router. So in a small home or a SOHO environment, small home, small office, home office environment, and smaller companies, you would see something like that, and that's perfectly fine. As you get into bigger networks though, you don't necessarily want your edge router, which is, the entry point to your network, to also be the IP address that all your clients are using to access the internet and internet services. So in bigger environments, you typically have other IP addresses solely used for this dynamic path, so all of your clients can access the internet and not using the edge router's IP address. For this particular lab, either option will work, right? We'll be able to achieve success in either option. Just for kicks, we're going to use the NAT pool configuration option just because it's a little bit more involved. We're going to configure these three sections to configure a dynamic path. So the three sections to a dynamic path essentially follow this sequence, you could say. The first part is defining what we are translating. The second part is defining what we are translating it to. And then the last part ties these two commands together by telling the router, in this case, that whatever matches this ACL should be translated to this NAT pool. So with that said, we will start stepping through our configuration. So again, I'm going to do show IP NAT translations and show IP NAT statistics so we can start to see with what we have, and I can show you the operation of this and how these commands are going to change as we configure things. To start, I want to show you nothing underneath show IP NAT translations, and then over here, dynamic mappings, nothing underneath that. With that in mind, let's start with our configuration. So if I do, Conf T, IP access list, we'll make this a standard access list, and I'm going to call it dpat source, just because why not? And I'm going to say this access list is going to match any IP address in the 10.10.0.0/24 network. Yeah. Now I could also add the 1020 network. That would also allow the layer 3 switches to access the server through this translation. It's an option I have if I needed to. If I do show access list, this is the ACL that I've just created, and that takes care of the first part of configuring a dynamic path. This is me telling the router what I'm going to translate. The next part is this part in here where I'm going to tell the router what I'm going to translate it to. And that's done using a NAT pool. So IP NAT pool, I'm going to call this dpat pool. Excuse me. Now I have to list the start IP address and end IP address. Now in this case, we're only going to have one IP address that we're translating these packets to. And again, the instructions don't necessarily give us one that we have to use, so I'm just going to pick one. We're going to pick 23.1.2.99. But I have to list a start and end IP address, so I'm just going to list this twice to say start on this IP address, end on this IP address. That's how I tell it to only have one IP address in the pool. Now, at this point, if I hit the question mark, you'll notice that it tells me the next option I have is to add a net mask. But my little command guide here indicates that I can add the command prefix length. Now this again is a packet tracerism. On a real router, I'd be able to use either the net mask command or the prefix length command. Now in both cases, those commands are doing the same thing. Remember, a subnet mask and a CIDR notation is really telling you a size of a particular network. What we have to do next is tell the router what size of network that the start IP and end IP fit within. Now, since we're just doing one IP address, anything, it doesn't really matter what we put here. One IP address is always in its own network, so we don't have to worry about it. But let's just say, oops, let's just retype all that. Let's just say dpat pool 23.1.2.99, 23.1.2.99. Let's just say I'm going to configure my start and end IP address in two different /24 networks. Now, if I did my net mask and I said that both those IP addresses happen to be in the same /24, it's going to error out. It's going to tell me, hey, wait a minute. These two are not actually in the same /24. That's the purpose of the second part of this command, where you do the net mask or where you do the prefix lengths on a real router. It's telling you, rather, it's sort of a validation to make sure that both these IP addresses do indeed fall within the network that you specify over here. If I do that same command and I specify a /16, now it'll take because these two are indeed in the same /16. But we actually don't want to do that. I just wanted to kind of show you the purpose of that command. So I'm going to know that out, and then I'm going to go back to it. We'll configure the mask to match the IP of this particular subnet, 23.1.2.24. And again, we're just going to have the same start and end IP. Make sure I didn't type anything. Cool. So now if I hit enter, that is going to be accepted, if you will. So now if I do my show run section IP NAT, hello Susmita, welcome to the stream. We have our NAT interfaces, which we applied earlier, and that still applies. We don't need to change those. Those are perfectly fine. And then we have the NAT pool we just configured. And then of course, not appearing here is the ACL that we configured earlier, because these lines don't include the string IP NAT, but that's still in place. So at this point, we have configured an ACL. That's the first part of the dynamic PAT configuration. We have configured a NAT pool. That's the second part. The last part is to simply tie them together using this command right here. Hello, Dan. Welcome. So that command is going to be IP NAT inside source. Actually, before we do that, let me quickly show you show IP NAT translations. Nothing is there. Show IP NAT statistics, and nothing is here, because you're going to see this command output is going to change in a moment. Again, what we're doing here is showing you the configuration, but this is right here showing you the operation. And again, that distinction is important. So let's configure IP NAT inside source. The ACL name, we called it right there, dpat sources, dpat sources. Nope, we called it dpat source, one S or no S. And then the pool we called dpat pool. Now, the last part is this overload command. Now, this overload command is actually very, very important. I'm going to show you the rest of this chart. Notice we are configuring a dynamic PAT. Down below is a configuration of a dynamic NAT. The only difference between this configuration and this configuration is the existence of the overload command. That overload command is what makes this a dynamic PAT and not a dynamic NAT. Now, I don't plan to get into the differences of dynamic NAT and dynamic PAT. I did write articles about that. Feel free to look those up, or I'll have links in the description when the live stream ends. But there is a big difference between a dynamic PAT with a P and a dynamic NAT with an N. And in this case, we definitely want a dynamic PAT with a P. So we definitely want this overload keyword. So let's not forget the overload keyword. I'll hit enter. And again, I'm going to do show IP NAT translations. Nothing here at the moment. I'll show that change in a moment. Show IP NAT statistics, however, is going to have something interesting. So this is where we typed the command in before. You'll notice over here, dynamic mappings, there was nothing afterwards. But now, underneath dynamic mapping, it's telling us we have a dynamic translation. Anything that matches the ACL DPAT source is going to be translated to the pool DPAT pool. And this is showing us some statistics of what's going on within that pool. Cool, so that is the configuration. So now let's actually test everything. Let's open up our PC. This is the failure condition from before. And let's see if now we can ping through. It looks like we can. So we have successfully configured our dynamic PAT so that our PC over here can indeed ping the web server. If we do this command again, notice over here we had allocated 0 of the 1 IP address in our pool, but now we have allocated 1 of the 1 IP address in our pool. So notice how that command changed when I started sending traffic. And then notice down here, show IP NAT translation showed us nothing. But if I do show IP NAT translation now, it's going to show us that 4 ICMP packets from the inside local 10.10.0.10 were translated to 23.1.2.99, which matches what we configured in our NAT pool. I can also do a TCP packet. Where'd my PC go? Oops. On port 80. Then go back over here and do my show IP NAT translations. And here is the TCP packet. Again, the PC's IP address was translated to our inside global. And this is proving to us that the NAT is indeed applying and working. Finally, the last thing that I'm going to show you, and this is just kind of like to go full circle with the lab objectives. The purpose of the lab objectives, was to open up this particular website, thekeithbarker.com, from the PC. So we'll close out the command prompt, go to the web browser, thekeithbarker.com, and you'll see that the web page loaded, which tells us we have successfully completed this lab. And that about covers it. That about covers it. Okay. So let me turn it over to the chat. Anybody have any questions over anything we did, or anything we verified or validated, or how we went about doing anything? Mention so in the chat. Otherwise, if you guys enjoyed that, let me know. Let me know what you guys thought. I'll use this as a break to sip some coffee. Cool. Cool. Well, that's awesome. Thank you. Glad you enjoyed it. Glad it was clear. It always makes me chuckle how big of a delay there is in the YouTube chat. The stream itself is only 2 to 3 seconds delay, which is perfectly reasonable, but the chat itself is like 15 to 20 second delayed. Cool. So Firmal asked a good question. If there's a second PC, does this mean that it'll have a different port number when pinging the server? Yes. In fact, I think we can actually, I know there's a way to duplicate a device. There it is. Let's actually do it. So let's connect this guy. Let's rather connect this guy to the switch. We're gonna have to make sure that the switch is configured so that the new port, oops, that's not the command I wanted. Cool. So this is already in VLAN 10. So probably this is PC, the original PC. This is showing connected, but in VLAN 1. So this is likely the new port. Actually, it is. It's showing you right there for the PC we just plugged in. So let's put that guy in the right VLAN. Int FA02 switch port mode access switch port access VLAN 10. Let's jump on this PC. That's correct. We're gonna have to give it a new IP address. We're gonna give it the IP address 10.10.10.12. Cool. And then we'll jump over here. Can we ping the router 10.20.0.1? There it is. Cool. It was doing ARP. And can we ping the server 23.1.2.2? Actually, before I do this, let's take a look at what we have. So there is my translations. Oh, that's interesting. What is going on with the UDP? Oh, it's DNS. Those are from PC1. All right, cool. So that's fine. We want that in place. Now, if I do, let's just start with a ping. So the ping was successful. If I do show IP NAT translations again, here are the pings from the new PC, notice .12 that we just added. Now, ICMP packets don't actually have port numbers. What this is right here, it's called the ICMP sequence number. It's just a number within the ICMP packet header, so you can track the messages so you can tie a particular response to a particular packet that was sent. That's what's going on in here. Actually, I have another video where I pick apart the show IP NAT translations output in great detail. I'll make sure that is linked in the description. But what you asked about is port numbers. So let's actually do that. So nothing. Cool. So notice right now, all of these ports, 10.0.26 through 10.0.30, are in use by PC1. So if on the second version of PC1, I do a telnet let's take a look at our command output. Oh, so okay, this is, where is it? Oh, no way. That's UDP. Let's do a few more. Yeah, let's check it out. So right here is the correlator, 1027. So right over here, PC1 sent a TCP packet with a source of 1027. At the time, that IP address, that port was still available, so the router gave it that port. But notice down in here, PC2 10.0.0.12 sent something with the same port number, but that port was not available, and so the router gave it a new port, 10.0.31 in this particular case. So that kind of proves formal question. I mean, the answer to your question was yes, formal, but hopefully this kind of proves it to you, so it's not just so you're not just taking my word for it rather. But do keep in mind, so if we look right over here, no wait, right, let me see, I know we saw it. Yeah, so right in here, PC2 used the port 10.0.25. At that time, whenever that packet made it through, that port number was available, so the router didn't change the port. So the router's only going to change the port if necessary, if you will. If you are interested, I did create this video some time ago. It picks apart what a static NAT is. Oh, that's not the one we want. We want the other one. We want this guy, configuration and verification. I did pick apart static NAT, how to configure it, but then also we set up this lab and I showed you the command as it, the packets as they went through. This is the packet capture before, this is the packet capture after, and we picked this apart to great detail. So if you're interested in that, I'm going to throw the link in the chat. Cool. I don't see any other questions, so I think at this point that wraps it up. So if there's no other questions, rather, if there are more questions, feel free to mention something in the chat room. Otherwise, let's go back to this guy right in here. Cool. Well, hopefully you guys enjoyed that. That, I guess, wraps up what we were planning to do. In the lab, we went through a bunch of different commands. We kind of looked at all these commands. I guess we didn't do show IP protocols, but we did all those other ones, and we showed you how those work and showed you the operation and configuration of each and the differences. Hopefully that's something you guys enjoyed. This is something I'm planning to do on the regular if you guys are interested. So if you are interested, you definitely have to let me know. Mention something in the comments below. All the resources we talked through insofar as Keith's site and the playlists and the NAT configuration guide I put out in the video I was just talking about. I'll add links to the description to this video after the live stream ends. It'll be in the description right next to the like button and the subscribe button. Hint, hint. So definitely check those out if you guys want. Otherwise, if you guys have more labs you want me to work through together, definitely let me know. Definitely provide the links to those labs, and then we will go from there. So Dan asked, what is the next lab I'm planning to do? So this is the next one I'm planning to do. It's going to be a much more involved lab. I haven't put it out on YouTube yet. I just created the little thumbnail, if you will. Oh man, I do not like Windows arrow, whatever. But that's what it's going to be about. It's a more involved lab, but we'll be configuring a bunch of different things: VLANs, DHCP, DHCP relay, trunking, SVIs, and so on. So that is the plan. I got to open up all my windows again. Cool. Oh, you guys don't see the image because my screen share was disabled. Let's try that again. This is what the new lab is going to be on. And likely it's going to be Thursday morning. So about this same time as this time, this coming Thursday. But I'll post about it on Reddit, or I'll definitely schedule this out in advance so you'll see this. Cool. Awesome. Well, I'm glad you guys enjoyed it. Thanks for coming out. Thanks for hanging out. This was a good time. Yeah, I guess we'll see you guys in the next live stream on Thursday. Otherwise, appreciate y'all's time. Hopefully you guys enjoyed this. Hopefully you got something out of it. Thank you for watching, and we'll see you next time. Bye, guys.